Astronomers watching 3I Atlas, that moment arrived the instant the sun finally moved out of the way and the James Webb Space Telescope locked onto its position. The interstellar visitor had returned, but this time it was blazing at more than 400% of its previous brightness, as if during those hidden months behind solar glare, something fundamental had changed. Webb recorded a glow that didn't act like dust scattering sunlight or frozen gases sublimating into space. It moved in smooth, intentional waves, almost as if the surface was adjusting itself to the heat pouring from our star. When astronomers sharpened those images, pushing Webb's capabilities to their limits, a new shape rose beneath that reflective layer. Perfect hexagons aligned in what looked disturbingly like a metallic grid, a pattern far too clean, far too orderly, for anything that should be drifting naturally through deep space. And before anyone could fully process that discovery, another signal appeared. A faint ultraviolet flash pulsing every 247 seconds, with timing so precise it felt closer to a coded transmission than any natural cycle we'd ever observed. None of this fits the profile of a comet. None of it matches anything we thought we understood about interstellar visitors. So if 3I Atlas came back glowing harder, sharper, and more controlled than ever, one question now hangs over everything. Why did it return at all? And if you believe discovery begins where certainty ends, hit subscribe. That's where our universe gets interesting. Because what happened next rewrites everything we thought we knew about the visitor that made everyone pay attention, long before 3I Atlas burst back into view with its impossible brightness. It had already earned a place in the short and deeply mysterious history of interstellar visitors. Only two objects had ever crossed into our solar system before it. The first was Oumuamua in 2017, that cigar-shaped traveler that left scientists arguing for years about what it truly was, its strange acceleration, its unusual tumbling, its complete lack of a visible coma. The second was Borisov in 2019, a more conventional icy comet that brightened, burned, and slipped away following predictable physics. When 3I Atlas appeared, it became the third confirmed interstellar object humanity had ever detected. And that alone was enough to make every major observatory turn its full attention toward it. In the months leading up to its disappearance behind the sun, coordination was extraordinary. Hubble tracked it. The Keck Observatory in Hawaii captured nightly observations. Multiple ground-based telescopes across Europe recorded its motion with meticulous precision. This level of coordination wasn't routine. Astronomers don't normally follow a comet this closely, unless something about it feels fundamentally off. And with 3I Atlas, that unease began almost immediately. Its orbit didn't behave like normal comets from our neighborhood. Its brightness changed in ways models couldn't fully explain. Even when observatories compared notes, sharing data across continents and time zones, the readings refused to settle into any familiar pattern. Nothing about its path matched the graceful arcs we see in long-period comets drifting in from the outer edges of the solar system. Instead, its course looked sharper, almost deliberate, like it was responding to forces that weren't in any textbook. The more scientists watched, the stranger it felt. Some nights, the light curve dipped deeper than any model predicted. Other nights, it brightened too quickly, accelerating through luminosity changes that should have taken weeks. Every attempt to fit the readings into standard equations left behind more questions than answers. Yet the global network kept tracking it. Because once something arrives from another star system, you don't look away. You can't afford to. And then, just as the data started hinting at a deeper puzzle, 3I Atlas vanished behind the sun. All anyone could do was wait. When 3I Atlas finally emerged from behind the sun, the first numbers that came in stunned every team watching. Its reflected light had jumped more than 400%. Not a gradual brightening as fresh ice got exposed to solar heating. Not a moderate increase as dust lifted off the surface. A spike so dramatic it looked like the object had been turned on like a switch. Natural comets brighten when they heat up, absolutely, but they don't suddenly transform into cosmic mirrors. Yet that was exactly what the James Webb readings showed. The object wasn't just brighter, it was reflecting light as if its surface had been polished, reconfigured, fundamentally altered during those months it spent hidden from view. As analysts compared the incoming data streams, something even stranger appeared beneath that brightness spike. The surface temperature of 3I Atlas held steady. It didn't climb the way normal comets do when swinging close to the sun. It didn't cool off when moving farther away into the outer system. Instead, it behaved like a system actively managing heat, keeping itself within a controlled range no matter where it moved in its orbit. For astronomers used to watching comets flare unpredictably, chaotically shedding material as thermal stress cracks their surfaces, this kind of stability felt deeply, fundamentally wrong. The more they examined the light curve, the more the pattern looked deliberate. Brightness would rise and fall in smooth transitions, not the chaotic bursts you'd expect from random outgassing. The reflective layer responded to sunlight in ways that reminded some researchers of adjustable panels, the kind you'd find on spacecraft designed to regulate temperature through controlled exposure. With each rotation, different sections seemed to angle themselves toward or away from incoming solar radiation. It was almost like watching a machine regulate its exposure, shifting its skin to balance temperature and illumination with purpose rather than accident. Telescopes across the world tried desperately to find natural explanations. Dust jets don't move this evenly. Ice vents don't create such stable, repeating light patterns. No comet ever observed has kept its temperature locked while displaying such dramatic changes in reflectivity. Whatever the surface of 3I Atlas was doing, it wasn't following the rules of thermal physics that govern frozen bodies drifting between stars. And then there was the structure beneath the glow. As those bright reflections flickered and shifted, glimpses of something more rigid occasionally appeared. Underlying segments that seemed to shift in perfect unison, moving together as if connected by something more sophisticated than random geology. Observers compared the behavior to solar panels rotating to regulate heat on satellites, to the controlled surfaces on deep space probes designed to maintain stable internal temperatures. While no one could definitively confirm what they were seeing through the glare and distance, the possibility alone was enough to unsettle teams watching the live feeds. When astronomers finally managed to sharpen the Webb images, pushing through layers of brightness and glare, something emerged that shouldn't exist on any natural object. Perfect hexagons, aligned in a metallic grid pattern across what appeared to be the surface layer. Not approximate hexagons, not roughly six-sided structures that might result from crystal formation or thermal cracking. Perfect geometric shapes arranged with precision that looked engineered rather than evolved. Natural formations create hexagons sometimes. Basalt columns on Earth, certain crystal structures, even some ice formations under specific conditions. But those natural hexagons are irregular, imperfect, vary in size and alignment. The pattern on 3I Atlas showed none of that natural variation. Each hexagon matched its neighbors. The grid alignment held across the visible surface. The metallic signature suggested refined materials, not the rocky, icy mixture you'd expect from a body formed in the frozen outer reaches of another star system. Teams ran analysis after analysis, looking for any natural process that could produce this geometry. Thermal stress patterns? Wrong symmetry. Crystal formation during freezing? Wrong scale and consistency. Impact cratering? Completely wrong morphology. The hexagonal grid looked manufactured. And that realization sent quiet alarm through research groups who'd spent careers studying natural solar system objects. As 3I Atlas swept closer to the sun during its approach, astronomers expected the usual spectacle. Natural comets build long tails stretching away from sunlight as dust and gas get pushed outward by solar radiation. It's one of the most predictable behaviors in the entire solar system, as reliable as gravity itself. But 3I Atlas refused to follow those rules. Instead of trailing behind it in the expected direction, the stream of material pointed directly toward the sun. A clean, narrow anti-tail forming in the one direction no comet tail should ever go. At first, some researchers wondered if viewing angle was creating an illusion. Comet tails can appear distorted depending on observation perspective, but when data from Hubble arrived, it showed the same forward-streaming plume. Keck Observatory in Hawaii confirmed the identical impossible orientation. Several European observatories added their own measurements. Every telescope, from every angle, saw the same thing. This wasn't observational error. This was something happening on the object itself. The anti-tail didn't drift or waver randomly. It held a surprisingly stable line toward the sun, as if guided by a force stronger than radiation pressure. Natural gas jets don't behave this way. They scatter as comets spin. They burst from weak spots in surfaces. They don't lock into precise directions with such consistency. Yet the plume from 3I Atlas looked anchored, like it was reacting to an internal push rather than being blown outward by external forces. Scientists tried explaining it through orbital mechanics. They ran simulations. They checked for unusual rotations or asymmetric plumes. None of the models matched what telescopes were seeing. The behavior required something that overpowered the sun's influence, something pushing material outward with deliberate force. As days passed, the consistency of the anti-tail became even more unsettling. With each rotation, the stream tightened instead of diffusing. It realigned again and again with the sun's direction in a way that made it look coordinated, controlled, intentional. Observers compared the pattern to thruster plumes on spacecraft, not to natural geysers from a comet core. The resemblance was impossible to ignore. When 3I Atlas came back into view after solar conjunction, astronomers expected strange light patterns, maybe another brightness burst or new jets. What they didn't expect was a signal. The object began emitting ultraviolet flashes at perfectly timed intervals, repeating every 247 seconds without drifting even a fraction of a second off rhythm. Natural objects flicker. They fluctuate. Rotation causes periodic variations, but those variations drift over time as spin rates change. Nothing in nature keeps time like a metronome with mechanical precision. Yet 3I Atlas pulsed with the accuracy of a machine that knew exactly what it was doing. When the data was processed and the pattern analyzed, something even more astonishing emerged. The first flashes mapped directly onto the sequence of prime numbers, 2, 3, 5, 7, 11, and onward in perfect mathematical order. This wasn't noise. It wasn't random fluctuation or coincidental timing. It was a mathematical signature. The kind that nature doesn't produce on its own, the kind that SETI researchers have spent decades hoping to find in radio signals from distant stars. Prime numbers are universal. They're the building blocks of arithmetic, the same in any mathematical system anywhere in the universe. And in the search for extraterrestrial intelligence, they're considered one of the clearest ways a civilization might announce its presence to others capable of recognizing the pattern. But the signal didn't stop there. As the ultraviolet pulses continued beyond the prime sequence, the final burst stretched on far longer than any previous one. For 13 minutes and 37 seconds, 3I Atlas emitted a continuous UV stream unlike anything recorded before. When scientists converted the wavelength variations within that extended pulse into visual data, the pattern formed a spiral. Not just any spiral, but one aligned with the golden ratio. The same mathematical structure found in galaxies, in hurricanes, in the arrangement of seeds in sunflowers, in the proportions of living organisms across Earth. Embedded inside that spiral were binary markers, repeating in loops that looked intentional, structured, almost like instructions designed to be decoded by anyone capable of receiving them. SETI researchers who'd spent decades listening for radio signals immediately recognized the implications. A sequence of prime numbers is extraordinary on its own, but a binary spiral keyed to the golden ratio? That matches the very template SETI uses when teaching what a deliberate extraterrestrial message might look like. In internal discussions, several researchers quietly referred to the pattern as a possible intelligence signature, though no one was ready to say it publicly, with careers and reputations on the line. When the ultraviolet signal finally faded, astronomers expected 3I Atlas to continue along its predicted path, drifting into the outer darkness the way all comets eventually do, their activity fading as they move away from solar heating. Instead, the object made one final move that stunned every observatory watching. Its trajectory shifted by a tiny but undeniable margin, just 0.09 degrees. Under normal circumstances, that adjustment would mean nothing, well within measurement, error, or natural variation. But for an interstellar object with no engines, no guidance system, and no known natural process capable of steering it with that precision, the maneuver was impossible to ignore. Moments later, its speed began to climb, not gradually through the slow push of solar radiation or gravity assists, but in a clean, accelerating curve that sent it outward faster than models allowed, moving as though it had completed whatever purpose brought it here in the first place. For scientists who'd spent months tracking its impossible brightness, its metallic hexagonal structure, its hollow shell, its directed jets, and its coded ultraviolet pulse, the timing felt too precise to be accidental. It appeared, revealed, pieces of itself step by step, transmitted something mathematical, and then, without waiting for any response, pivoted toward interstellar space and accelerated away. If 3I Atlas truly is technology, then it didn't just pass through our sky. It studied us. It watched how we reacted. And once it finished, it slipped back into the void, the way a probe would after completing an observation mission. The final question remains: did we just witness an unusually bright comet with a string of improbable coincidences? Or did we watch the quiet departure of a device built by another civilization, one that came to see if anyone was watching back?